Hey everyone, today we're going to finish up, module 2. So this will lead you to your quiz, hopefully. So let's take a look. Let me share some stuff with you. Okay, so a little while back, we left off with the library functions. Okay, in our last video we talked very briefly about it. Let's talk a little bit more about it. So the first one we see, the top left here, when f of x equals a number, we have a horizontal line. Now from that, if we add x and multiply x by a constant number, we can manipulate that line, change its slope, its attitude, if you will, its steepness, okay? Either way though, the linear function goes from negative infinity to positive infinity as far as a range. If it's just a constant value, it's that constant value. I'm sorry, it goes from negative infinity to positive infinity as a domain. As a range, if it's just a constant value, it remains that constant value. However, if we add an x to it and multiply x by some value, it changes that line. It makes it diagonal, if you will, and that will change the range to all real numbers. Okay? The parabola, or quadratic, fits a function f of x equals x squared. All parabolas and x squares have a similar shape. Their steepness might be a little different, might be upside down, but they all have a similar shape. For the parabola, the standard parabola of x squared, the range and domain are this. The domain is all real numbers, negative infinity to positive infinity, and the range goes from 0 upward, so 0 to positive infinity. The square root function, we look at the square root function, we cover up this left-hand side of the parabola, and we take the right-hand side and twist it or turn it and put it over on its side, we get this, interestingly enough. And that, the domain starts at 0, because you can't have a negative underneath the square root, and goes to positive infinity. The range does the same. The absolute value function has exactly the same range and domain as the quadratic. The cubic function has no restrictions. The domain is all the real numbers, negative infinity to positive infinity, and so is the range. If we take the cubic function, we twist it, and we turn it on its side, we get the cube root function. The cube root function also has no restrictions on the domain or range, negative infinity to positive infinity for both. Then we have the reciprocal function, or sometimes called the inverse function, on our library. And we'll add more to our library eventually, but this is the start. Okay, the problem with the reciprocal or inverse function is when you have a 0 in a denominator, you have to skip over it. Okay, so the domain would be all of the values except when the denominator equals 0. So when it's 1 over x, when x is equal to 0, the denominator equals 0. So our domain goes from negative infinity to 0, not including 0, union with 0 on the other side, not including 0, to positive infinity. Then the range, if we look here, it looks like we're skipping over the x-axis here, and we are. And it gets really close to the x-axis, but it doesn't ever cross it. Okay? And so since that's the case, we go from negative infinity to 0 for the range, not including 0, skip over 0, go from 0 to positive infinity. So we're going to use this library of graphs throughout the rest of the semester. Let's take a look at some domains and ranges. Okay, linear, quadratic, absolute value, cubic, cube root functions, again, have no restriction on the domain or on the range, other than, the basics. So in other words, where it starts. Okay, so with the quadratic function or with the absolute value function, in standard, they start at 0 and go upward for the range. Okay? However, the square root function and the inverse function do. Let's take a look. So for the square root function, we cannot have a 0 in the denominator. So I'll take a look at this one example, and then you can read through the other one. F of x equals the square root of 3x plus 2. So we want to make sure that 3x plus 2 is greater than or equal to 0. So we set up the inequality, and we solve for x. Solving for x, this means we start at minus 2 over 3 because it's less than, or greater than rather, or equal to, and we go to positive infinity. For the inverse function, or the reciprocal function, let's start with 3 over 2x plus 1. This means 2x plus 1 cannot equal 0. So when we solve for x, that means x cannot equal minus 1 over 2. So now we have to skip over minus 1 over 2. So that means we start at negative infinity to minus 1 over 2, not including minus 1 over 2, so we have the parenthesis. And then we take the union of minus 1 over 2, not including it, to positive infinity. Each place we skip, each point we skip that makes the denominator 0 in an inverse or reciprocal function, we do that. We do exactly that. So if I had another point here of, say, 2, I would go from negative infinity to 2, and then I would skip over 2 with the union symbol and go from 2 to positive infinity. Okay? Or in this case, I would just do the in between, okay, if I had more than 2. Okay? And we see that sort of up here. Okay? Not quite the same application, but close. All right, so now I'm going to take a look now at some other properties of functions. This is a PDF that you're going to be sent with this video in your news items. In this PDF, we deal with extrema, local mins, maxes, increase, decrease type of function if we can determine it. Sometimes we can, sometimes we can't. And then domain and range. Okay, so the first one I'm looking at, okay, is example 1. Now we can see that's a quadratic. Okay, we can see that the domain is all real numbers. The range starts here at 3 and goes upward, so from 3 to positive infinity. Now, what are local maxes and mins? Local maxes and mins are low points and high points on the graph. So we have no high point on this graph, where the graph kind of rounds up and then goes back down, but we do have a low point here at x equals 0. So at x equals 0, we have a local min. Okay, now, if that's the smallest the function can absolutely positively be, it becomes the absolute min. And in this case, it is. Decrease, we always talk about decreasing from left to right. So left to right, as we go downward, it's going downward, the graph, all the way to 3. So back here, negative infinity, can't be there, but, so we leave that as a parenthesis, to 3. At 3, it does neither. It levels out. So we go from negative infinity to 0, not 3. At 0, it levels out. X equals 0. We always talk about it in terms of x. Okay? So we don't include 0. Then from 0 to the right, it goes upward, so it's increasing. So again, leave 0 open to positive infinity. Let's look at the next one. The next one is a cubic function. It matches the cubic graph idea. Up, 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 then levels out, maybe goes up and down a little bit, then back up. Okay, that's the cubic. Okay, so now in this cubic function, okay, we have a local min or low point right here at x equal b. We have a local maximum or high point where it levels off and then goes back down at x equal a. So we have a max at a and a min at b. Notice when I talk about the minimum and maximum, I'm talking about the x value. If I want to know what the value of that is, then I figure that out later. But when we talk about mins and maxes, we talk about where they are in terms of x. The same idea for increasing and decreasing. So now, are there any absolute mins and maxes here? The answer is no, because it keeps going down, 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 down to negative infinity. If it did that, there's no minimum. Same thing here with it going up, 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 up to positive infinity. There's no absolute max, okay? Since you can't ever get to negative infinity or positive infinity. All right, so now where's it decrease? So again, we go left to right. So remember at A, at these mins and maxes, it doesn't do either. So we start at A, not including A, and go to B. It goes downward from A to B. So open parenthesis at A because we can't include it, and open parenthesis at B. Where does it increase? Well, it starts back here at negative infinity and goes up, up, up to A. Not including A, because again, it levels off. It doesn't either increase or decrease there. It's a local min. Okay, so from negative infinity to A, we're increasing. Then it starts up again at B and goes to positive infinity, but it starts around B, not quite at B. So we leave it open. So we have negative infinity to A, union B to positive infinity. Our domain and range are all real numbers because it's a cubic. For example 3, we cannot really determine what type of function it is. Okay? We don't know. We don't have enough of the picture. But we do know that it's a closed and bounded function. Okay? Any function that starts and ends at a specific point is closed. And as long as it doesn't go up, up, up forever or down, down, down forever, it's bounded. And so for here, we start at x equals 0 to 17 for the domain. Okay. The range looks like it starts at 1 and goes up to 15. So we have a local min at x equals 17, and over here a local min at x equals 0. Those are the low points of the graph, if you will. Okay. Now we talk about local, that means around that point, around this point, like a neighborhood, as close as you want to get. What's the behavior of the graph? It becomes the minimum values around that point. There's a local max around that point at x equal 9. Now, as it turns out, the smallest this function can be is here at 17. So there's a local min at x equals 17. Its value is 1, but there's a local min there. There's a local max at x equal 9. Its value is 15. Now, since this one at 17 is the smallest on this range that x can be, that means it's the absolute min. And here at x equal 9, since it's the largest x can be, or the function can be, I should say, that's our absolute max. It decreases from 9 to 17, increases from 0 to 9. Now, it does include 5, and it does include 17. It does not include 9, however. And our last one here is another cubic. And again, we have a local min and max. We have a local max at -3, min at 3. Neither are absolute. Decreases between -3 and 3. Increases from negative infinity to -3. And then increases again from 3 to positive infinity. Our domain and range are all reals because it's a cubic. Now, let's take a look at something else. It's going to take me a second to find here because I just realized I don't have it handy. So hang on a second. Bear with me for just 1 minute here. Be patient. Let's see here. Here it is. This is the handout I've sent to you already. So let's scroll down this a bit. Let's see if we can't finish this off today. Right, the next thing we want to talk about is what a piecewise function is. A piecewise defined function. A piecewise defined function is defined within certain domains, certain parameters. Okay, so what we see first off with the piecewise function is that if you really want to take a look and understand piecewise functions, start with this length. Okay, that's a graph that deals with piecewise functions. It deals with evaluating and with calculating at particular points. So what's a piecewise function? Again, it's a function that's defined over a certain range. So let's look at our first piecewise function. It says f of x equals x for x that's less than or equal to 2. As soon as we hit 2, anything above that, we jump down to the next function, 2x minus 1, for x greater than 2. So if we're asked to find f of -1, since f of -1 is less than or equal to 2, we use x. So f of -1, plug -1 in for x, and we get -1. F of 2, since x is less than or equal to 2, at 2 it's equal to, so we still use x. At 3, if we wanted to evaluate f of 3, we evaluate it by plugging 3 in for x and get 2 times 3 minus 1, or 5. Why? Well, because x is greater than 2. Okay? I'm going to send out some PDFs for you in the next day that describe some graphs and how I graph them, a couple of piecewise defined functions. Okay? Let's talk about average rates of change. Okay, so the average rate of change is like the slope of the line. So let's take a look at f of x equals x squared minus 6. We want to find the average rate of change for the function between x equal 2 and x equal 4. So really what we're doing is we're calculating the slope of the line between x equal 2 and x equal 4. In order to do that, a slope of a line needs to have y values. So to find the y values, we plug 2 into f, evaluate, and we get minus 2 out. And we plug 4 in for f into x for f, and we get 10. So that means we're really finding the slope of the line between 2 minus 2 and 4, 10. So we apply the slope formula and get 6. So that means the average rate of change for that function is 6 between those 2 points. Sometimes what we see is we see what's called a difference quotient. This is very confusing for college algebra students. So let's take a look at how we would do this. So this is the difference quotient, f of x plus h minus f of x over h. How do we use it? Well, the first thing we do is we find f of x plus h. Then we find f of x plus h minus f of x. And then we divide whatever we have in 2 by h. So let's take a look at an example. We're going to use the difference quotient for f of x equals 2x plus 3. So the first thing we're going to do is we're going to find f of x plus h. So that means we plug x plus h in for x here. So that means we have 2 times the quantity x plus h, again, substitute with parentheses, plus 3. We distribute the 2 to simplify, and we get 2x plus 2h plus 3. That's all the further we can go with that right now. Now, the second step, we're going to take what we got in part 1 and subtract off f of x. So to do that, again, here's what we got in part 1, minus, and again, when you substitute, put parentheses around things. So we're substituting f of x in, so 2x plus 3 is in parentheses. Distribute the parentheses, we get 2x plus 2h plus 3 minus 2x minus 3. Combine the 2 x's, combine the 3's, and we end up with 2h. Then we're going to take 2h and divide it by h, and that gives us 2. Okay. Hopefully this helps you out a little bit. And again, expect tomorrow some graphics related to piecewise defined functions. Also be looking for these other items that I talked about today attached to your news item. Have a good day. Hope this helped.